Okay guys, so we would like to evaluate the infinite sum of -1 to the power of k plus 1 all over k, which is the infinite harmonic alternating sum. Well, the convergence of this series right there is actually guaranteed by quite a few convergence theorems, so I'm not gonna be really going through that stuff. I'm just gonna let you guys let you guys out the proof, and well, I think it's quite beautiful. So, well, one more caveat, I'm not gonna be trying to explain how the guy who came up with this proof, for the first time actually could, for some reason, think of all the stuff he did. I have no idea, honestly, so I'm just gonna, tell you the proof, and hopefully we'll all enjoy its beauty. Yes, so we are supposed to calculate the sum as k goes from 1 to infinity of -1 to the power of k plus 1 all over k. So let's start with recalling what the sum of a finite geometric series actually is. Yeah, so whenever we have a sum, let's call it maybe S. That sum is equal to 1 plus x plus some x squared all the way up to some x to the power of n minus 1. And then I am going to make myself another sum S, but this time I'm gonna multiply it through by an x, by one more x. Yeah, so I'm gonna multiply multiply this sum through by an x. So each and every one of those components of that sum, each and every one of those terms that sum is gonna be multiplied by an additional x. Yes, I'm gonna just bump up each and every one of those powers by a factor of 1. So 1 is gonna become an x, then x is gonna become an x squared is gonna become x cubed, so on until x to the power of n minus 1 is going to become x to the power of n. Now, if I were to go on and nicely subtract those two sums from each other, I'm going to get s minus s multiplied by that x. That's going to be equal to, and now, pretty nicely, this x right there is gonna cancel out with this x right here. This x squared is gonna cancel out with this x squared there. There's gonna be some x cubed to cancel out with x cubed there. And also here we will have some x to the power of n minus 1 that's gonna cancel out with this x to the power of n minus 1 here. So the only thing that's gonna be left is just 1 minus x to the power of n. But now just dividing both sides by 1 minus x, factoring s out of here and just dividing everything by 1 minus x, we will get that s is actually nicely equal to 1 minus x to the power of n all over 1 minus x. And so we will pretty nicely get that, well, by what we just achieved here, we can say that the sum as k goes from 1 up to n minus 1 of x to the power of k is equal to 1 minus x to the power of n all over 1 minus x. And so we can just kind of treat this, let's say, as a function and plug in the value of -x as opposed to just a plain old x. Yeah? So let's go on and do that. We're gonna achieve the sum as k goes from 1 up to n minus 1, once again, of a -x to the power of k being equal to 1 minus x to the power of n all over 1 plus x, so 1 minus x, yeah? But now we can rewrite this entire fraction there as just a sum of two fractions, which are as follows: 1 over 1 plus x, and then minus -x to the power of n all over 1 plus x, pretty nicely. But now we'd like to take this fraction on the left and just take it to the left-hand side of our equation. So what we're gonna be left with after doing that is the sum that goes from 1 up to n minus 1 of -x to the power of k minus 1 over 1 plus x is equal to -x to the power of n all over 1 plus x. And now for some reason we are supposed to take the definite integral from 0 to 1 of both sides of this equation. So we would like to go on and evaluate the integral, or maybe I will change the color for now. Yeah, so it's going to be the integral from 0 to 1 of the sum minus the integral from 0 to 1 of that 1 over 1 plus x is equal to the integral, now the integral from 0 to 1 of the -x to the power of n 1 over x, and I also should be writing those dx's when I'm applying integrals. Lovely. But now, well, notice that this sum right there is finite. N is just a finite thing, and just this entire formula only holds for finite numbers, yeah, only for finite values of n. So it would be pretty nice to go on and just change the order of summation here. We don't really care about having a finite sum inside of an integral. We can just take it out, and so taking out the sum and the -1 to the power of k in this case, we will be left with the sum as k goes from 1 up to n minus 1 of -1 to the power of k multiplied by the integral from 0 to 1 of negative x, sorry, not negative anymore, but just positive x to the power of k dx, and then nothing changes here in this integral from 0 to 1 of the reciprocal of 1 plus x. And then on the right hand side, I'm just gonna kind of take out the -1 to the power of n from that thing. Oh, and I'm very sorry, I did not write the negative sign here, which definitely was there. Lovely. So now we will get the integral from 0 to 1 of, oh, I should have left more space there, so -1 to the power of n plus 1 integrals from 0 to 1 of x to the power of n all over 1 plus x dx. Lovely. And now evaluating all that stuff, well, we see that this integral from 0 to 1 of x to the power of k is just gonna be x to the power of k plus 1 divided by k plus 1 evaluated between 0 and 1. So that's going to be just 1 all over k plus 1 minus 0 over k plus 1. So that's just going to be, well, 1 over k plus 1. I'm going to write it down here pretty nicely. 1 over 1 plus k. Lovely. And now this integral there. Well, from 0 to 1 of the reciprocal of 1 plus x, the antiderivative of 1 over 1 plus x is just the natural log of 1 plus x. And so it's just going to be the natural log of the absolute value of 1 plus x in the bounds of 0 and 1. That's going to be natural log of 2 minus natural log of 1, but natural log of 1 is just a 0, so we will end up with just the natural log of 2. And this integral right there, we are not going to be evaluating at this for now. I mean, it's also pretty tough, so let's just leave it. Okay, so what we are left with then? We're left with, first of all, the sum as k goes from 1 up to n minus 1 of -1 to the power of k all over k plus 1. Guess what this sum is? This is exactly the sum we were trying to evaluate, but with a small with a slight difference that this is a finite sum and we're looking for the infinite version of it. Yeah, it doesn't matter at all. And it also starts with a 1, but well, slight difference. Okay, so and then what we'll get is this negative natural log of 2, and it's all equal to -1 to the power of n plus 1 of the integral of x to the power of n all over 1 plus x dx. But, well, if those two numbers are equal to each other, the absolute values also have to be equal to each other. So we can just, go on and take the absolute value on both sides of this equation. There is no problem to take an absolute value. There is only a problem in, well, getting rid of it afterwards, yeah. So, well, now, if we took this absolute value, we can just kind of get rid of this -1 to the power of n plus 1. I mean, no matter what it is, even if it's negative, we will cancel it out anyway, because we applied this entire, not modulus, we applied this entire absolute value, yeah? So we can just say that the absolute value of this sum from k equal to 1 up to n minus 1 of -1 to the power of k plus 1 minus the natural log of 2 is equal to the absolute value of that integral from 0 to 1 of x to the power of n all over 1 plus x dx. But, well, one more thing, this entire thing, those two things are gonna be actually greater than or equal to 0, because always absolute values are gonna be greater than or equal to 0. Lovely. Okay, but now we can use the, I think it's triangle inequality for integrals, but no idea. I think I learned about it in metric spaces. Anyway, so we have this inequality that the absolute value of an integral is less than or equal to the integral of the absolute value of the integrand. So I'm going to just say that those two things are less than or equal to the integral from 0 to 1 of the absolute value of x to the power of n all over 1 plus x dx. But one more thing, I mean, whenever x is between 0 and 1, it's pretty lovely because 1 plus x is always greater than 1. So we can kind of say that this entire thing just has to be less than or equal to the integral, the integral from 0 to 1 of just x to the power of n. I can drop the absolute value sign. So, well, why is it so? Why is it less than or equal to this x to the power of n? Well, I'm not dividing by anything that's greater than 1, so it should be greater, shouldn't it? Yeah, so what we'll actually get is that, well, this absolute value of the sum from k being equal to 1 up to n minus 1 of negative 1 to the power of k all over k plus 1 and minus, it's pretty important, this negative natural log of 2 is gonna be less than or equal to the integral between 0 and 1 of x to the power of n, but this thing is just 1 over 1 plus n. Yeah, so that's just 1 over n plus 1. Just take the antiderivative and plug in those values for n. And now, well, we are actually trying to get the infinite version of this sequence here. So it would be pretty nice to just take the limit of everything that we've got here. So, well, let's go on and do it. I'm gonna take myself the limit as n approaches infinity of this entire inequality. So 0 is less than or equal to the sum as k goes from 1 up to n minus 1 of negative 1 to the power of k all over k plus 1 and then minus the natural log of 2. I should have written it in the absolute value, natural log of 2, which is less than or equal to 1 over n plus 1. But now, well, as n goes to infinity, 0 is just a 0, but 1 over n plus 1 goes to 0. And so, well, we've got squeeze theorem or just sheer logic. Well, this guy right there is less than or equal to 0 and greater than, sorry, it's less than or equal to 0 or greater than or equal to 0 at the same time. It just has to be equal to 0. And so we've got that this thing is equal to 0. We've got that the absolute value of the sum we're looking for minus the natural log of 2 is equal to 0. And so we've got that, pretty nicely, the limit as n approaches infinity of the sum that we're looking for, k plus 1 is equal to the natural log of 2, which is exactly what we were supposed to find. Okay guys, so I really hope you enjoyed this video. If you did, then like and subscribe to my channel not to miss out on any stuff I'm posting daily, and we'll see you in the next one. Bye.